Welcome to lecture 16. In this lecture, we will give a final example of amortized analysis. We will describe a problem called dynamic array. We will study the scenario where there is only insert operation first, and after that, we will talk about how to handle both insert and delete operations at the same time. So recall that an array is a very simple data structure that supports order one-time random access. And sometimes, given a certain array, we want its size to be flexible so that from time to time, items can be inserted to the array or items can be deleted from the array. So for instance, we may want to use an array to implement a binary heap as we have already done so previously. And the size of the array may change over time. And in such a case, we call this a dynamic array problem. Now, what actually is the problem? So here, suppose that we have allocated some space for the array at the beginning, and in case we have allocated too much space, then there could be a waste when the array doesn't have many items at all. So instead, what we may do here is we may first allocate a fixed amount of space to it, not very much, but a small amount of space at the beginning. But when the space is not enough after some insertions, we will relocate the items of the current array and move it to a larger array so that we can accept more insertions in the future. Now, in such a case, we could have better space usage because we are not going to waste a lot of space even when the array is containing very few items. But there is a drawback, or there is a trade-off. We will need to move the items around when this relocation event occurs. So let's say we will really want to have good space usage. So the problem here is that is it possible that the items will not be needed to move around very often in this scheme? So let's consider what we can do as follows. So first of all, suppose that K is the current array size. Let's say the array suddenly becomes full after a certain insert operation. What we will do here is we will reallocate. So we will make a new array. The array size is equal to 2k, which is the double of the original array size. And then we will move all the items in the array into this new array. So whenever there is this relocation event, the size of the array will be doubled. And suppose that at the beginning, we allocate a fixed amount of space, let's say 100 units of space for 100 items. So what we know here is if we apply this scheme, so the array will normally be at least half full unless it is not that full when we are in the initial state where the number of items is less than 100. So we will either be wasting at most 100 units of space, so this is a constant amount of space at the beginning, but after that, at most half of the space is wasted because we can guarantee that the array is always half full when we have more than 100 items. So in such a case, we will have a good space usage compared to the case where we may have unbounded waste. Okay, so let's take a look let's measure how frequent or what is the time that we are wasting in moving the items around. Okay, so let's say there are altogether n insert operations performed. Now the total cost of these n operations will be equal to n because there is at least a cost of 1 for each operation and an extra of the cost for moving the items around. So we will need to add the number of times an item is moved. Now, using the previous scheme, we will see that when we have 100 items, so after 100 insertions, the initial array will become full. And in that case, we will move the items, reallocate to a larger array of size 200. So there will be 100 items moved at the 100th operation. But after that, we will need to wait until the 200th operation for the next relocation event. And, and when that happens, 200 items will be moved. And after that, we will need until we are at the 400th operation, and in that case, 400 items will be moved. So the number of times an item is moved is equal to 100 plus 200 plus 400 up to whatever that is less than or equal to n. So 100, 200, 400, 800, and so on and so forth. And we can easily calculate that. The sum of all these movements is at most 2 times n. So what does that mean? The total cost will be equal to n plus a number that is at most 2 times n. So the total cost is at most 3n. Or in other words, the amortized cost for insert is only order 1. So on average, for each insertion, only one item is moved. Now, the previous analysis method is actually the aggregate method. Now, for this problem, we may actually use accounting method as well. So for accounting method, what we need to do here is we first set the amortized cost for the operation and then show that at any time, the amortized cost together with the bank savings is enough to pay for each operation. So we now set the amortized cost for insert to be equal to $3. We have two cases to analyze. So whether after the insertion the array becomes full or after the insertion the array is still not full. So let's look at the case when the array is not full after the insertion, because this is a simpler case. Now, if this happens, then we will see that there is no item movement at all. Yeah, because the array is still not full, no relocation event. We are paying $3 for the amortized cost, but because this operation there is no item movement, we just need to spend $1 on the actual cost, putting the item into the array. That's all. And then we have $2 left. So these $2 are stored as excess. To have a better accounting of where the money is stored, we will associate this $2 to the item we have just inserted. So now, what we have here is each item that is inserted since the last movement. So we may have from time to time some movement, some relocation event. But after the relocation event and before the next relocation event, items may be inserted, and for each item inserted during this time, it will have an associated $2 there. Okay, now let us take a look of the other scenario, which happens when the array becomes full after insertion. Now, if the array is full after insertion, let's say K denotes the current array size. What we know here is that when it is full after insertion, relocation event occurs, but then there must always be at least K over 2 items inserted since the last relocation event, since the last movement event. So in that case, these K over 2 items that are inserted since the last movement, each will have $2 there for the excess. So altogether, there will be K dollars in total for the excess stored by these items. And these K dollars will be enough actually to pay for the movement. So we can use all the excess of these K over 2 items and to pay. And then after that, all the excess will be used up after the movement. But we don't care, okay? If we ever have some other insertions after that, we will have excess only for those that is inserted after the movement. So it is okay to use up all the excess after the movement here. But so far, this is the dynamic array problem half solved because we have just only handled the insert operation only. Now to handle the delete operation as well, we will modify the scheme slightly as follows. So again, we will use K to denote the current array size. And same as before, if the array becomes full after insert, we will double the size of the array, create a new array with size 2k, and relocate all the items to the new array. Now, the next part handles what happens for the delete. Okay, so if the array becomes only 25% full after delete, a quarter full after delete, then this time we will create a new array, this time with array size k over 2. And then relocate all the remaining items of this array into this new array. So the purpose of this one here is that because the array is now only a quarter full, it is rather empty now. So we will try to use a smaller array instead so that we will have better space usage case. So more precisely, suppose that at the beginning, we will allocate a fixed amount of space for the array, and then we will see that unless the number of items is less than 100, the array is always at least a quarter full. So if it is at least a quarter full, then only 75% of the space are wasted. It looks a little bit bad, but it's not that bad. It is because only a fixed portion of or a fixed ratio of the space is wasted. So whenever we have wasted space, we will guarantee that there are always enough number of items there that is really being stored. So it is not too bad for the space usage. And now let us analyze the amortized cost for the insert and the amortized cost for the delete operation. Now we will use accounting method again. For inserts, actually it is the same as before. We are going to set $3 as the amortized cost for insertion. So if the array is not full, no movement, $1 pays for the actual cost, while we can have $2 save on the item that is being inserted. On the other hand, if the array is full, then we can see that at least k over 2 items are inserted since the last movement. So in that case, these excess stored along with these items will be enough to pay for the movement here. So this part is for insert. Now how about delete? Okay, so here the amortized cost for delete, we can set it to be $2. So again, when the array is not 25% full after delete, so it means that, okay, it's not that empty. Then there will be no movement. Okay. Now, when there is no movement, $1 will be paid for the actual cost, and then now $1 will be stored as an excess. So here, this is tricky. The excess is here not associated with an item, but this excess is associated with a deleted item somehow. Although it's not there, but then whenever there is a deletion, there is $1 saved. On the other hand, when the array becomes 25% full after the deletion, so in that case, we need to handle the relocation. So if k denotes the current size, then we will see that at least k over 4 items are deleted since the last movement. So when there are k over 4 items deleted, we will have an excess of k over 4 in total. This will be enough to pay for the movement of this 25% of this array, k over 4, to the new array. So in that case, it is also okay. So indeed, the above analysis, we are using the accounting method. We may also use aggregate method, but then perhaps the argument will be a little bit messy. And as we have mentioned before, potential method and accounting method, they are just like two sides of the same coin. one is the complement of the other. So we may also use potential method to analyze the amortized cost for the operations. Here, the potential function we may set to be something like this. It depends whether the current status of the array is more than half full or if it is less than half full. If it is more than half full, we will set the potential function to be equal to 2 times the number of items minus k over 2. So this is this one. On the other hand, if the array is at most half full, then in that case, the potential is equal to k over 2 minus the number of items in the array. So when the array is exactly half full, then we will see that the potential function here is equal to 0, both of the case. But then, using potential method, although it works, it is not very intuitive. So by far, the best way to analyze the performance of this dynamic array seems to be the accounting method. So that's the end of the discussion on the amortized analysis.